Even though our galaxy could have as many as 100 billion planets, a new study suggests that only 300 million of them might be able to support life. Some of them are only 30 light years away from us, and some are almost lifelike replicas of our home planet Earth. Astronomers have discovered two distant exoplanets, each around 100 light years from Earth, and one of them could have aliens on its surface. The outer planet resides towards the inner boundary of what is deemed the habitable zone, much as Earth is, says Amaury Triaud, an exoplanet expert and a member of the team that made the historic discovery. A planet in the habitable zone around its star could have liquid water on its surface. Triaud has found that this one has the second best chance of having life of all the exoplanets in the habitable zones. The planet is around 40% larger than Earth and orbits its star every 8.5 days. Many scientists forecast the planet to be rocky. Its size alone suggests that this is the case. So far, no non-rocky exoplanets smaller than 1.4 times Earth's radius have been found. The planet is tidally locked to its star, meaning that opposing sides of the planet experience continuous daylight and darkness. As Dustin Jones pointed out, this planet is just 3.9 million miles from the Sun, compared to Earth's 93 million miles from our Sun. The exoplanet may still have conditions conducive to life despite its proximity to the star it orbits. Another reason is that despite its proximity, the Sun of another world is roughly 6.5 times smaller and half as hot as ours. However, astronomer Beth Biller from the University of Edinburgh in the United Kingdom has pointed out several features that may be detrimental to the planet's habitability. The planet's size and the possibility that it receives intense radiation from its tight orbit around the star makes it a poor candidate for supporting life. The exoplanet was found using the Speculus telescopes. First, they utilized the Transiting Exoplanets Survey to confirm the long-standing hunch that there was a second planet in this distant solar system. However, because of the planet's close proximity to its star, scientists first discounted the likelihood of life there. And when they started looking, they found something amazing. Tests can find planets by measuring how much their host stars dim. According to NPR, TESS has picked up the dimming of a star caused by a planet transiting in front or behind it. As a result of their enhanced sensitivity to infrared light, the ground-based Speculus telescopes then follow up to confirm the finding. The newly found planet is in the habitable zone of a cold star, which emits mostly infrared radiation. The next step is to use the James Webb Space Telescope to peer at the planet and identify any traces of its atmosphere. As reported by Inverse, Webb may provide insight into the exoplanet's habitability. At the same time, new telescopes are being built on every continent, ushering in a revolutionary era in astronomy that will unveil the universe's origins. Next-generation telescopes with such innovative designs are imminent and could help us find life on other planets immensely. If finished, ELT will be the largest optical-range ground-based observatory in the world. A gigantic 80-meter-tall, 6,100-ton rotating dome serves as the showpiece. The 88-meter diameter dome chamber is about the size of a football field. There will be a 39-meter main mirror in the dome's center, comprised of 798 separate hexagonal pieces with a combined area of 978 meters squared and a weight of 132 tons. To ensure controlled functioning, high-precision sensors will constantly adjust optical alignment. As a result, the observatory will be able to gather 15 times as much light as the most powerful optical telescopes available today. To adequately correct for image distortion brought on by Earth's atmosphere, the ELT was designed with a brand new adaptive optical technology in mind. Scientists can directly watch new planetary systems form and take pictures of these planets and their atmospheres. They will also be able to measure how fast the universe is expanding. It wasn't until February 2022 that the skeletal structure of the ELT was completed. This would allow construction on the dome's structure to begin, which is where the ELT would be housed in the long run. Satellite images may be compared over the next few months to monitor the observatory's progress. By 2027, scientists want to have the ELT fully functional, and there are even more giants on the way. This is the massive Magellan Telescope. After preparations are complete, the giant Magellan Telescope will survey the heavens from high above the Atacama Desert in Chile, a region renowned for its stellar astronomical conditions. 7 main mirrors will be used to focus light from the universe into the detectors of the optical infrared telescope. With a height of 12 stories, it far surpasses any other telescope in size and scope. Each with a diameter of more than 8 meters, the specifications indicate that the GMT telescope will be 10 times more powerful than Hubble and 4 times more potent than the JWST. It will use a wide variety of equipment to study topics like the evolution of the galaxy, gravitational waves, and easily detectable objects in the near-infrared, such as planetary systems and the existence of biosignatures in their atmospheres. The construction of the telescope is expected to be completed in 2029. More giants are lining up to zoom in on habitable planets. Additionally, the Legacy Survey of Space and Time, formerly known as the Large Synoptic Survey Telescope, is now under construction in the Atacama Desert. This telescope will eventually house the world's largest digital camera with a resolution of 3.2 billion pixels. Every night, 15 terabytes of data will be recorded. Everything about the objects in the sky will be documented, including their size, location, and shape. To create a high-definition video of the universe, astronomers must repeatedly display a vast region of the sky. In contrast to previous telescopes, LSST will picture the whole of the night sky, not just a selected few things. By doing so, the results from the other telescopes may be put into a geographical perspective. Imagine yourself utilizing the newest Xbox system on a first-generation TV. In this case, the Xbox would try to send high-resolution graphics with lots of colors to the TV, but the TV wouldn't be able to handle them. You won't be able to enjoy what the Xbox offers unless you also have a display with a similar level of detail. The same method used to check for exoplanets' opacity is used to examine massive amounts of photon data from space. The opacity of a solid is a measure of how easy it is for photons to pass through it. It depends on the light's wavelength, the material temperature and pressure, and outside conditions. This means that the makeup of the exoplanet's atmosphere may be inferred from the imprint left behind by each photon when it collides with an atom or molecule. By extrapolating light from data, scientists may deduce the makeup of an exoplanet's atmosphere. The James Webb Space Telescope acts as a detector liaison in this case. However, a recent study indicated that while evaluating the most prevalent opacity model, the JWST light data hit an accuracy wall. Scientists argue their model needs to be more sensitive to tell the difference between a planet's atmosphere being 300 or 600 Kelvin, or between having 5% or 25% of a given gas. Nirala claims that the statistical significance of this discrepancy matters for us to constrain planetary formation processes and reliably discover biosignatures. To avoid the situation where we don't find ourselves seeing something lovely with JWST but not knowing how to interpret it, we need to work on our interpretive abilities. The team also realized that its models were masking its data quality. Subtle alterations are all that's needed to mask failure and pass it off as success when none exists. We found enough factors to adjust, even with a defective model, to get a fair match. We could do more if we knew just how light and matter interact. It's commonly known that this holds true for Earth's atmosphere. Still, the rules vary, and the data with higher quality that we risk misinterpreting grows substantially while exploring other habitats. For much that Webb will improve the accuracy of our information, our translation approach will hamper us from finding out important information, such as whether or not a planet is livable. In other words, we need to improve our models so we don't overlook the intricacy of data. Given the fascinating nature of our JWST results, the team has suggested looking into the possibility of combining astronomy and spectroscopy to produce more accurate opacity models and prepare to see what could be the first aliens on exoplanets. Do we need a more powerful telescope to find aliens, or is there something we are missing? Tell us in the comments. Be sure to subscribe, and I'll see you next time.